All right, so finally, moving into the complex part of complex analysis. So chapter 7, complex functions. My goal here in this short video is to get us to the point where the new material actually is, because the first couple sections of this is actually a review, well, or a corollary to things we've already done over the A calculus. I mentioned in class that this is the usual definition of complex derivative, right? We have a difference quotient, just like Calc 1. It satisfies linearity, you can pull constants out, you got a chain rule, great. You got a power law. Now, that said, it's not all fun and games. I mean, if you actually try to calculate the the derivative of the complex exponential directly from the definition, you get into it, you find yourself faced with these as your real and imaginary component functions that you got to take the limit as h goes to 0 of. I mean, I don't know about you, but these are kind of scary to me. I mean, sine's going to 0, that's going to 0, that's going to 0. These are bad. But this is why the Cauchy-Riemann equations are so beautiful. So let me just, right here, next to this, show you how this would be, how we can show that ddz of e to the z is complex differentiable in the Cauchy-Riemann. Actually, instead of doing that, let me just write it like this here. So e to the z we have defined as e to the x cosine y plus I e to the x sine y. So this is u and this is v. If we calculate partial y of e to the z, right, we get what? Oh, I'm sorry. I'm still. It's the A calculus. It's influencing me too much. Let's just do ux equals to what? It's e to the x cosine y. I'll try to be normal for once. Vx equals to what? E to the x sine y. What's uy? Uy minus e to the x sine y. What's vy? Vy e to the x cosine y, right? By the way, continuous on the whole complex plane. Am I right? You know I'm right. These are continuous functions of x and y anywhere you go. And also observe that ux is equal to vy, right? And Vx is equal to minus uy. So therefore the Cauchy-Riemann equations hold. For continuously differentiable f of z equals to e to the z. Therefore df dz is just equal to partial f partial x. And so, what is that? Well, d dz of e to the z is equal to, well, what's partial f partial x? It would be ux plus I vx, which by the way is e to the x cosine y plus I e to the x sine y. Wait a minute, that's e to the z. So, surprise, surprise, the derivative of the complex exponential with respect to a complex variable is, in fact, the complex exponential again. No limits to be seen. Simply an identification of continuous differentiability, verification of the Cauchy-Riemann equations, and bam, there you have it. That is why we like the Cauchy-Riemann equations, because we all believe in death to limits. Alright, anyway. Sorry, let me not dance on the grave of limits just yet. They do matter from time to time, but this matters more. F is holomorphic on a domain D if it's complex differentiable at each point in D. We say F is holomorphic at Z0 if there exists an open disk centered at Z0 on which F restricted to that disk is holomorphic. So what does domain mean? what's domain? Remember, a domain is a open connected set, right? So, all right. We'll be using this terminology from here on out, okay? So I may ask you a quiz sometime soon to define holomorphic for me, all right? Just a possibility. Anyway, moving along, this calculation here shows that the f of z equals z bar is in fact nowhere differentiable because it fails. Well, I actually calculate the limits because I don't know why. I guess I'm just trying to show a limiting calculation, but it's much easier. I mean, come on. At this point in our life, if we want to show that f of z equals z bar is not complex differentiable, how about we just do this? Partial f partial z bar is partial z bar, which we have shown is 1, which is not equal to 0 for all z in C. Therefore, f of z equal to z bar is nowhere complex differentiable. Which means, of course, it is also nowhere holomorphic. It is possible to have a function which is holomorphic and yet it's possible to have a function which is complex differentiable at some points, but is not holomorphic. Because holomorphic requires complex differentiability on some open set. And so this function is actually complex differentiable on the coordinate axes, but it's nowhere holomorphic because anytime you pick a point, you can't find a disk around it on which the function is complex differentiable in the whole disk because you're always off the coordinate axis where it's not complex differentiable. You know it fails to be complex differentiable off the coordinate axis because off the coordinate axis the Cauchy-Riemann equations fail. All right. I mean, let's see here. This is u. This is v. So like ux is 3x squared, y squared, and vy is, what is it? It is 3x squared, y squared. Well, this is not helping. Uy is 2x cubed y, and vy is 3x squared, y squared. So you can see that ux is not equal, excuse me, vx is not equal to minus uy, except on the coordinate axes, right? Vx, I'm sorry, I'm an idiot. Vx is not equal to minus uy, except when at least either x or y is 0. So you don't need to do any kind of fancy schmancy complex limit. We just look at the Cauchy-Riemann equations. They fail, so it's not complex differentiable at such points as the Cauchy-Riemann equations fail. Again, it's not if and only if the Cauchy-Riemann equations hold, it doesn't mean that it's complex differentiable unless we also have additional data, right? For example, continuous differentiability will suffice. This calculation right here, I think I've gone through before. Anyway, here's the Cauchy-Riemann equations. Oh, I actually go through the calculation of that one here. I wish I could remember that from when I looked at this 3 minutes ago, but oh well. I think we've gone through this calculation. It'd be good for you to look through this again. This, I believe, answers the question Sam was asking about whether or not, like the connection between complex differentiability and our other way of thinking. So here it is. If this Fauché coefficient holds, then this would be, then this would be that, and so we can rewrite this as that, which means that a plus ib is this, which is to say that goodness gracious, I forgot the name of this thing. This has to be equal to the complex derivative as it is. Oh, well, f prime of z naught would be that, and that's also equal to that. So in other words, it all's the a-differentiable notion and the difference quotient notion matches up in this way. All right. Anyway, long story short, theorem 7.23 gives us if we have complex differentiable at z naught, then it's real differentiable and the Cauchy-Riemann equations hold. This is very useful for disproving complex differentiability to point, because all we have to do is show the Cauchy-Riemann equations fail and it's not complex differentiable. That's nice. 2, if we have continuous differentiability and the Cauchy-Riemann equations hold at a point, then it's complex differentiable at that point. 3, if it's continuously differentiable on a domain, an open connected set, and the CR equations hold throughout, then that implies that F is holomorphic on D, which means that it is complex differentiable at each point in D. Finally, just a reminder, we can rewrite the Cauchy-Riemann equations like this, which is at times a very, very nice way to look at it. I already went through this example. Oh, I forgot to shade this definition. If we have a function that's holomorphic on the whole complex plane, it's said to be an entire function. This set of all entire functions is denoted like this. That's not an O, it's kind of like an O. I don't know what this thing is called. It's, I think it, well, anyway. I'll come up with a good name for it by next time. Don't worry. And then here's the sample calculation. We define sine of z to be that. And if we use the chain rule and the differentiation of the complex exponential we just derived, then you can put this stuff together and you get that the derivative of sine is cosine, which I mentioned is shocking. And very similar arguments will show you the derivative of cosine is minus sine, derivative of sinh is cos, derivative of cos is sinh. It's all good stuff. Maybe I will make some of these into homework that will be enjoyably simple. Finally, we mentioned before this theorem that if the gradient of a function was 0 on a connected set, then that forced the function to be constant on that set. Here's an application of that. So if we have the complex derivative is 0 for all z in a connected set, D is a domain, so it's connected, right? Then f is constant. So f prime of z is this, which means that ux and vx are 0, but by the Cauchy-Riemann equations, so is vy and uy, which means that the gradient of u and the gradient of v are both 0 on this connected open set, which means that both u and v must be constant, and hence f is constant. Pretty neat. So again, just to reiterate, if it's, oh, shnikes, analytic, I mean to write holomorphic. Sorry. You know, I originally was working from Gamelin, and Gamelin has used analytic in place of holomorphic where I really don't want it to be, so anyway, fixed. All right. And a related result, if f is holomorphic and real valued, it's constant. So real valued would mean that the v is 0, so f is just equal to u. So like ux is equal to v, well, vy is 0 and vx is 0, which means that ux is 0 and vy is minus vy is 0, which means that the gradient of u, well, anyway, we can see that f prime of z is 0, and so by the previous theorem it's constant. And there are a bunch of other related things, like if it's pure imaginary, holomorphic, sorry about that. Yeah, I'll be complaining about this here and there, I'm sorry about that. Of course, we could follow the usual Calculus 1 path and show you how to differentiate all your favorite reciprocal trig functions. Maybe I'll make some of these homework, it'd probably be good for you guys. And finally, the set of all holomorphic functions on a domain is denoted like that. I still don't, like I said, I'll come up with a name for it next time. The term holomorphic was actually given in 1875 by Briet and I guess Bouquet. And eventually I will explain the relation of the terms holomorphic, analytic, and conformal. Actually, Monday, I intend to talk about conformal. The next little section is on the Cauchy-Riemann equations and polar coordinates. I really don't care about that. I mean, they're nice to know. Here, wait a minute, where are they? Here they are, I guess, but, you know, here they are again. You can write them this way, that's kind of nice. df/dz is e to the minus I theta partial f partial I. There's the polar coordinates version of the Cauchy-Riemann equations, kind of cool. And, you know, you can do stuff like show the derivative of z squared is 2z with this kind of technology. It's kind of nice. Or derivative of log z is 1 over z is not too bad in this technology. But we're going to derive this a better way. So anyway, that brings us to Monday, question mark. So I am assuming class won't be canceled Monday, so we can start here Monday. Sorry for the extended length of the lecture. I hope you realize that basically what I was just saying in sections 7.1 and 7.2 is that we already have covered that stuff in previous lectures. So just to be clear, starting here Monday. Thanks, guys.